Okay, the electron configurations of ions. Now, when we've done the electron configurations of atoms, but if we have ions, either negative or positive ions, we have to add in or take away electrons from the electron configuration. So the best way to approach this is take fluorine first. It's 1s2, 2s2, 2p5. That's fluorine. And then we have fluoride. We've added one electron, so this becomes 1s2, 2s2, 2p6. So fairly simple. Sodium is 1s2, 2s2, whoops, 2p6, 3s1. So the removal of one electron, well, we're going to start on this end. We wouldn't take away the core electrons. We'd start here, so we take away that one. So sodium ion, so this is fluoride ion. Sodium ion is this. Notice that they have the same electron configuration. So when we're talking about ions, when we're talking about atoms, every atom has its own electron configuration. No two have the same. But when we're talking about ions, one atom might gain electrons, one might lose them, and they could end up with the same number of electrons. Different charges, different species, but same electron configuration. Nitrogen, start with, you should just do this out in this form. And then nitride, we're seeing we're adding 3 electrons, so the nitride ion would be 1s2, 2s2, 2p6. So all of these have the same are the same electron configuration, and it's the configuration of neon. And though I'm giving the answer away for the last page, or I think a couple of lectures from now, these are isoelectronic with neon. Neon, the neutral atom, has the same electron configuration, and there's no any element can be made into an ion that they'll be isoelectronic with neon. Some of them would be very, very unstable. For 20, I think that's calcium, we could, calcium plus 10 would be, I should say calcium 10 plus, would have 10 electrons, so it would have the same electron configuration as neon. Now this would be highly unstable, but it would certainly be one that would be isoelectronic with neon. Okay, 2. Give standard ions for all group A elements and their exceptions. The exceptions are the ones that we're going to focus on because you learned the basic rules in the previous class, and then we want to get closer to the truth. Now the truth is that 1A and 2A elements are 1A elements are all +1. That's still true. Lithium +1, sodium, so I just drew them all. Group 2A, they're all +2. So those are the same, no problem there. Group 3A, most likely you were just taught that boron is +3 because it's group 3A, and that just makes things easy. But there is no boron +3. So if you write boron +3 from here on in, that's incorrect. That's why I've just put a box around it, no charge. Aluminum is +3, gallium is +3, indium is +3, thallium is +3, but it also is +1. That's new. So I've put a box around each of the exceptions or the differences to what you've learned. Now let's look at thallium. It's a monster of an atom. It has 81 electrons, so I've drawn it with the abbreviated form here. But even with that, we have F and D orbitals here. It's a pretty large electron configuration anyway. Now we look at the valence electrons. We have 6s2, 6p1. If we take away those, then thallium becomes +3, as we'd expect, because it's in group 3A. But we can also just take away this one. If we take away this electron from one of the subshells, the remaining subshell is filled and relatively stable. Remember now, thallium has 81 electrons. Whether it loses 1 or loses 3, it's not as big of a deal as, say, nitrogen losing 1 or 3 electrons when it only has 7. So this thing, it's not that it doesn't care, but there is definitely not as much difference between losing 1 and 3 as it would for a smaller element. So when it loses 1 and becomes, when this one is gone, then it becomes a thallium +1. It's pretty happy with that. That's fine. That's a stable state. Stable enough to form ionic compounds. So you should know that one. Then we look at group 4A. Now we know it can go back and forth between +4, -4. I'm just going to stick with +4. Silicon can be +4. Let me make sure there is another possible exception there if they have it in. Yeah, and then, no, I got that. So silicon is +4, germanium is +4, tin is +4, lead is +4, but we also have tin +2 and lead +2. Now they have one more p electron. So for tin and lead, they'd end with p2. And that would just show that we're either getting rid of 2 electrons or a total of 4. So they either lose, now they have different numbers here, but tin and lead can either lose just the p electrons or the p and the s, just like with, analogous to what happened with thallium. And so we get these possibilities. We talked about these in the previous class. These are new. Make sure you know those. Then we go to group, let's go backwards here. Group 7A, they're all -1. Group 6A are all -2. Polonium can have plus charges, but we're not going to worry about that. Since polonium can be -2, it fits the bill, and that's fine. And I should just say that there are lots and lots of exceptions all through here. A lot of these lower levels, as we get lower on a group, they become more like metals, and they start to have more than one oxidation state. But these exceptions are good enough for now. So if you have a periodic table that shows you all the oxidation states, you might say, wow, it looks like everybody has an exception at the lower level, and that's true, but we're just going to worry about these. When we get to group 5A, you see they're all -3 until we get down to bismuth, which acts more like a metal, and it's +3. So there are lots of exceptions. These are the ones that we come across a lot. We use lead, bismuth, tin a great deal in our studies, and we talk about boron a lot because it's a small atom, small number of electrons, and it's a very useful one when we get to talking about structures. So we should know that it doesn't form ionic compounds. We don't really use thallium that much in our labs, but it's a good exception to know. Okay, now when we get to, we just talked about the group A's. Now if we talk about the group B elements, one thing that we find is that in the first row, this is true for the other rows as well, but we have iron can be +2 or iron 3. We know that. We've come across that quite a bit. But this +2 is true for cobalt. It's true for nickel. It's true for copper. And these are all in the same row. This is unusual. This isn't what happens in group A. As we move from, in the group A elements, as we move from group to group, we change the ionic charge on the common ions. Chromium can be +2. Chromium doesn't really, or at least I don't remember offhand, but manganese does. Titanium does. So in this row, and this is true of the other rows as well, we form a lot of +2 elements. So ionic, these are +2 ions. Now for the metals in the transition metal part of the periodic table, they can have more than one oxidation state. There's some exceptions to that. But so we should talk about that, why they can have more than one oxidation state. It's going to be similar to what we saw with thallium, but then we should also talk about why they all can be +2 in the same row. So looking at iron and cobalt, we'll just use those two as an example, but they all of these elements follow the same format because they all build up from the same thing. They all have argon as their noble gas core, and then they all have 4s2. Then the number of electrons differs. The number of d electrons differs at the end, but they all have 4s2. Now the thing is that removing d electrons is a little more difficult than removing the s electrons. The d electrons are part of a sublevel that has 5 orbitals, and there's a tendency for more stability in those d orbitals than the s. So iron will lose its s electrons to become iron +2. Cobalt will lose its 4s electrons to become cobalt +2. Same for all the other elements in the row. So the reason most of the transition elements can have a +2 charge is that they lose the s electrons first. It's just easier to get rid of them. I don't say 4s electrons because the group below are 5s and then 6s, so they can lose those s electrons first. Now let's look at iron again to see why there would be +2 and +3. Now we know that iron +2, you lose the s electrons, but +3, what happens is we will lose one of the d electrons, and that leaves, remember your orbital diagrams, that leaves 1, 2, 3, 4, 5. We had 6 electrons. If we remove 1 electron, we end up with a half-filled orbital for each orbital, and that's a very stable state. All of the orbitals being half-filled, or all of them being fully filled, those are two very stable states. So iron +4 doesn't really happen because you'd have to remove 1 electron, leaving 1 half-filled, and you can kind of see a symmetry there. And the universe does work off of a lot of these ideas of symmetry. If you remove 1 electron, then you have it's not as symmetrical as having 1 electron in each orbital, and there's a stability that's gained from having that symmetry. I'll explain the trends of the ionic radii. Okay, so we'll look at, go back here. So we talked about the atomic radii, and well, let's just do that. Lithium is larger than beryllium, which is larger than boron, which is larger than carbon, which is larger than nitrogen, all the way down. Even though we keep putting in more electrons, lithium has 3 electrons, neon has 10, lithium is actually larger than neon. But what about, that's for atoms. Well, lithium is +1 and beryllium is +2. And I said that boron doesn't form +3 normally as far as ionic compounds, but we can always ionize it. So even though this isn't something that is stable and will form compounds, we can strip away electrons from anything. So don't worry if, well, wait a minute, you said that boron doesn't form ions, so it doesn't normally do it, and it won't form compounds from it, ionic compounds, but we can still strip that away. And then carbon will make +4 because it can be -4 or +4. Then we have nitrogen is -3, oxygen -2, fluorine -1, and then neon is unaffected. So when we take away an electron from lithium, it's going to shrink because the size of the atom is due to the electrons. You take one away, not only are there fewer electrons to make the size of the atom, but now there's a +3 charge at the center working on 2 electrons rather than 3, so it shrinks. But the beryllium has lost 2 electrons, so it should shrink more because it's lost 2 electrons, and also the charge at the center is a +4 charge, so that should shrink more. So the lithium should be larger than the beryllium, and then boron should be smaller than the beryllium, and then carbon should be smaller than the boron ion. So we look at the charges. The higher the positive charge, the smaller it is. But then, so we pictured the lithium, and then beryllium, and then boron, and then carbon. Now nitrogen has 3 electrons. It has, not only is it a negatively charged ion, it has 3 extra electrons, so it becomes gigantic. I'm sure this is not to scale, but just the picture that we just then jump up, and then it shrinks back down. So we get what we see is that we get this drop, and then this sudden jump, and then a drop again. So the carbon would be much, much smaller than nitrogen, the nitride ion, I should say, and then this will be larger than oxygen, the oxygen or oxide, greater than fluoride, and then greater than neon. So we look at the charges. The lithium is going to be has only a +1 charge, beryllium +2, so smaller, +3, smaller still, +4, smaller still. Nitrogen, the nitride, gigantic, because it's -3, then -2, -1, and then back to a neutral atom. Okay, now name 3 ions that are isoelectronic with neon. We'll do argon, because I already talked about this in that previous, the first example, or first problem. So argon, I won't write out all the electron configuration, but argon has 18 electrons. That's what isoelectronic means. Iso means the same, so same number of electrons. Looking at chloride, chlorine has 17 electrons, but chloride would have 18. Since it's right next to argon, adding 1 electron to it gives it 18 electrons. They both have the same electron configuration. Sulfur has 16 electrons, so sulfide has 2 more, so 18. Phosphorus is 15 electrons, so 18. You go from the other direction. Potassium has 19 electrons, a +1 makes it 18. So I'm doing more than 3 ions. Calcium is +2, so 18. It had 20 electrons, now it's down to 18. You can do something really wild. Let's see, 98, so californium +80 would have 18 electrons. So on my exam, if I ask you for 3 ions that are isoelectronic with a noble gas, you can give me anything you want, any element. You could do hydrogen, which would be 17, oops, 71, 17 minus, would have 18 electrons. Now, obviously, neither of these is particularly stable, but I didn't ask that. I asked you to give me 3 ions that are isoelectronic with argon. So as long as so if you want to mess around and come up with some that are bizarre, just make sure you're right. Don't make it californium 90 plus and then you'll be off, or make this hydrogen -7 and be off. Make sure that you're right. I don't mind sorting through it, an ion that you create, as long as it's correct.